What's up, everyone? Welcome back to the Math Corner. Today, we'll learn about how to evaluate limits. So let's get started. Okay, so the first method for evaluating limits is direct substitution. So if I have the limit as x approaches a of f of x, sometimes I can evaluate that limit by just computing f of a. All right? This does not work always, but this works a lot of the times. And it's the first thing you should try doing if you're given a limit problem, like a question that asks you to evaluate a limit. An example of when this works is if I have the limit as x approaches 2 of x cubed plus 1 divided by x plus 1. What I'm going to do is I'm going to plug in 2 for x. So I'm going to get 2 cubed plus 1 divided by 2 plus 1. That's going to equal 9/3, which is equal to 3. Okay? And if you see in the graph below, you'll see that that is true actually. The limit as x approaches 2 of x cubed plus 1 divided by x plus 1 is equal to 3. Okay? However, sometimes, like I just said like a minute ago, direct substitution does not work. Okay? Why? Well, I'm about to show you the two different cases where it doesn't. So the first case is if you get a denominator that's equal to 0. Okay, so if I evaluate the limit, if I try evaluating the limit as x approaches -1 using direct substitution, what's gonna happen? I'm gonna get -1 cubed plus 1 divided by -1 plus 1. What's that equal to? That's equal to 0/0. Okay. I cannot say that this limit equals 0/0 because 0/0 is just undefined. Okay? That it's not an actual number. So that's why I can't use direct substitution in this case. And actually, the limit is 3. Alright, believe it or not, the limit is 3, not 0/0. The second case where you cannot use direct substitution is if you have a negative under a square root. So if I have the limit x approaches 5 of the square root of x minus 6, if I try to calculate by direct substitution, if I try to evaluate the limit using direct substitution, I'm going to plug in 5 here. I'm going to get square root of 5 minus 6, which just equals square root of 1. But this square root of 1, I can't write that as the limit, okay? This doesn't apply to only square roots. This also applies to 4th roots, 6th roots, 8th roots, any like radical with even power. So like this is the second root. The same applies for the 4th root, 6th root, you know what I mean. Okay? But if I have a negative under this root, an even root, then I cannot use direct substitution to solve for that limit. And actually, this limit doesn't exist because this is outside of the function's domain anyways. So, previously, I gave you the problem limit as x approaches -1 of x cubed plus 1 divided by x plus 1. And I use this problem as an example to prove that direct substitution doesn't always work, all right? Because when I directly substitute -1 into this function, I just get 0/0. All right? Now, there's something special about the 0/0. The special thing is, if it's 0/0, this tells you that this limit is actually in its indeterminate form. All right? A 0/0 tells us that there might be a chance that if we rewrite or simplify this function and then plug in -1 once again into the newly written function, we might be able to get a finite number, or we might be able to make out if it's a vertical asymptote, all right? And when I did that on my notebook, I got the answer as -3, all right? So now I'm going to show you how to do just that, okay? So let's start. So we have the limit as x approaches -1 of x cubed plus 1 divided by x plus 1, okay? This is equal to the limit as x approaches -1 of x plus 1 multiplied by x squared minus x plus 1 divided by x plus 1. Okay? This is the difference of cubes identity. If you remember, we can rewrite x cubed plus 1 as this. Okay? So now, if we cancel this, we remove the denominator, or at least remove the factor on the denominator that makes this indeterminate, right? So when we cancel those two terms out that are making this function 0 over 0, when I plug in -1 directly, I'm going to get the limit as x approaches -1 of x squared minus x plus 1, okay? What's the difference between this and this function? Can you tell me? The function on the top is the exact same as the function on the bottom, except there's a hole at x equals -1. All right? Pat yourself on the back if you got that, okay? So, I can now evaluate this limit once again by simply plugging in -1 into this newly written function. All right, and I get 3 for the answer, okay? So this is one way we can solve for the limit. We can factor out, cancel, reevaluate, directly substitute once again into the newly written function. These are just one of many ways we can rewrite the function so that we can actually evaluate it. But they all involve some sort of canceling, okay? Like, we're gonna evaluate a few more methods using trigonometry, conjugates, and etc. But they all involve some sort of canceling of terms. Okay, so let's explore new ways to evaluate limits. So if we're given the limit as x approaches 0 of screw 1 plus x minus screw 1 minus x divided by x, how would you evaluate that limit first of all? If you try direct substitution, that's good, because direct substitution is what you want to start off with. Okay, so you plug in 0 for x, you get square root of 1 minus square root of 1 divided by 0, which equals 0 over 0. Now, what does 0 over 0 tell us? 0 over 0 tells us that the limit is indeterminate right now. So there is something that we have to cancel from both the numerator and the denominator to help us evaluate the limit. Okay, we have to cancel out something. Can you factor something out to cancel? No, it doesn't look like that. So, what we can do is we can rationalize the numerator. So, how do we rationalize it? We would multiply it by the conjugate. So we get 1 plus x minus square root of 1 plus x minus square root of 1 minus x divided by x. And then you're going to multiply that with the conjugate, square root of 1 plus x plus square root of 1 minus x. Okay, if we multiply the numerator with the conjugate, we also got to multiply the denominator by the conjugate so that the function remains the same. Because otherwise, if we only multiply the numerator with a conjugate, the whole function is just going to turn out completely differently. So that's why we got to multiply both the top and the bottom with the conjugate. So what do we get after multiplying the top and the bottom with the conjugate? We get square root 1 plus x squared minus square root 1 minus x squared divided by x times square root 1 plus x plus square root 1 minus x. All right? What does that simplify to? Well, I'm going to quickly erase this. That simplifies to 1 plus x minus 1 minus x divided by x times square root 1 plus x plus square root 1 minus x. What does that simplify to? That simplifies to 2x divided by x times square root, that was way too big, square root 1 plus x plus square root 1 minus x. All right? Now, what do you see here that we can do to help evaluate our limit in the bottom corner right here? I am just quickly erasing all my work. We can now cross out the x's from both the top and the bottom. Right. So now by crossing out the x from the top and the bottom, we will no longer get a 0 over 0 whenever we directly substitute 0 for x. So now the limit as x approaches 0 of square root of 1 plus x divided minus square root of 1 minus x divided by x, that's now the same as the limit as x approaches 0 times, the limit as x approaches 0 of 2 divided by square root 1 plus x plus square root 1 minus x. Okay, these two limits are the same. And actually, these two functions are the exact same, except the function on the right doesn't have a hole at x equals 0. Okay? So let's go evaluate this limit using direct substitution. What happens when you plug in 0 for x in the second function? We get 2 divided by square root of 1 plus square root of 1, which equals 2 over 2, which equals 1. All right? That took a really long time. But this is how you can use rationalization and then simplify the rest of your function to help evaluate limits. All right? So you rationalize, simplify, cancel, then direct substitution. That is how you use rationalization to help solve for limits. And remember, this does not only work for the numerator. You can rationalize the denominator the exact same way that I just did with the numerator. Do your simplification, cancel out the common factors, reevaluate the limit, and then, get your answer. So that's how you can use rationalization to help solve for limits.